everybody. Just to review a little bit of Activity 32's beginning lessons that we talked about prior to going on break, we covered 32.1 and 32.2. So what I've done here is I've pulled up my notes answer key so you can hopefully follow along with your notes as well from the Springboard book. Now, the big idea of 32.1 was introducing us to the idea of a vector, which is a mathematical quantity that has both magnitude and direction. Now, the magnitude is going to be characterized by basically the length. If you want to think of it like Pythagorean theorem, the length of this different piece here. So kind of like here's our magnitude, that length, and the magnitude is found by plugging into this formula. It looks very similar to when we solved for the r value. So the square root of a squared plus b squared. Now, where do a and b come from? Well, that's that directional component, which we call component form, which you will see right here. The component form, notice it has pointed brackets as opposed to parentheses. That's telling us that A is the horizontal movement, B is the vertical movement for the component form. Down below, we had some examples here, both given in the book and that we drew in of different pieces here. Now, one of the big things we talked about was standard form, and standard form is when its tail is at the origin, and that's your starting point, and the head then is going to be the arrow portion of this. So anytime you say it's the tail is the starting point, the head is kind of where the arrow is going to. We always talk in this class, tail to head is our directional value of these. So there's some examples on that. Now, moving forward from there, we talked about finding the component form. Again, the directional value of the point is with parentheses. The component form, how much it's moving left and down in this case for vector u, is represented with the brackets that are pointed like so, right? A comma b. Now, let's say they don't give you the picture so you can count left and right and up and down for A and B. You're going to subtract each time head minus tail, right? Not tail minus head minus tail to get those forms. So if you'll notice down below, we have some examples of figuring out if vectors are equal to each other. Vectors are equal only if their component forms are the exact same. Magnitudes might be the same, right, but they have to be going in the same direction in order to be considered equal. So we talked about in these couple examples here for A and B, those examples. Okay, and again, down here, example C is a great example of using what we talked about up above, head minus tail. So taking the head coordinate and then minus the tail coordinate to find A, and then also doing that same thing, head coordinate minus tail coordinate to find your B component. Okay. Finally, kind of to finish off with that piece, we did a little bit more practice with finding the component form using an example. Notice it starts at the bottom of this page, that example, using the head and tail values from here in number 1. They ask us to find the component form of that in 2A, and then 2B asks us to find the magnitude. Now, from your exit slips that you guys did prior to going on to break, a lot of you, when you plugged this in your calculator, were forgetting to use parentheses here around the negative. When you type this in your calculator, it is extremely important that you use parentheses, because if you do not, you are going to get answers that are incorrect. So for instance, on this one here, notice the correct answer is going to be square root of 48 squared plus parentheses negative 55 squared. If you do not type this in with parentheses, so let's say we just do 48 squared plus negative 55 squared, notice that answer is, first off, not even real. It's not even going to give us an answer in this particular problem, but it's incorrect. So just keep that in mind moving forward. That's kind of the major thing I saw going on with some of your exit slips on these type of problems. Okay, and that was this first part here. Again, it is important to note one last thing from the check your understanding, that while the magnitudes here would be the same, they are not going to be the same vector. They're not going to be equal in length because that directional value was not the same. It was -5 versus positive 5 and positive 4 versus negative 4. So be careful with that. Now we also talked about lesson 32 too, and that's starting to get into our different vector operations, including adding and subtracting. So using the picture here, we were able to talk about vector u in this picture and vector v in this picture, and we wrote down the component forms of those, how much they are moving. And then we talked about this distance between them, this final, if we just went from tail to head, and this last piece here, this is vector u plus v. And we talked about how this then results in the addition of our 2a components and the addition of our 2b components to get us our what we call resultant vector. Okay? So we are able to add those two together to get our final resultant. And we did not focus so much on the geometric portion of this, but what we did focus then was on practicing algebraically or symbolically, as the book likes to call it, adding vector addition for A and vector addition for B. Again, don't really worry about the geometric component of it. Worry about being able to add up your 2A components, add up your 2B components to get your resultant vector. Now from there we tested some things out. Looking back at this example that they gave us in example A using vectors u and v, we calculated the magnitude for u, the magnitude for v, and then we also added u plus v together and calculated that magnitude. Notice that that magnitude of each individual magnitude added together is not the same as that resultant vector's magnitude. So using from up above again the example they had, when we found the magnitude of 7, 2, not the same as the two individuals added together. So when they ask you for the magnitude of u plus v, it is different than just taking the magnitude of u plus the magnitude of v. Now moving on to number 8, we talked about subtraction. So the additive inverse is basically negating signage-wise your given. So the additive inverse of vector w is basically flip-flopping your signs down below. Okay. Looking then on to 9 and 10, we talk about actually doing that vector subtraction, which is really the same thing as doing vector adding, but with adding the additive inverse. So if you're not going to find the additive inverse first, what you need to be careful of, it's almost like subtracting negative values with polynomials. So for instance, like we were taking vector s minus vector t, you want to remember to distribute this negative to both pieces when you're adding them, okay, to get your resultant vector. Now, make sure you are aware doing vector s minus vector t is very different than doing t minus s because your resulting signages are different, right, in each one you do. So it is important for order which one you are subtracting, so be very careful of that. Finally, we talked about a little bit geometrically and symbolically scalar multiplication with vectors. So imagine if we were taking 3u, so u, vector u plus vector u plus vector u, and add those together, and symbolically this is what it would look like. Well, that's the same thing as just saying 3 times vector u. So when you are doing scalar multiplication with vectors, geometrically and more importantly symbolically, which is what we focused on, symbolically it's like distributing into your component form or vectors. Okay. Now, unlike when we were doing addition, when you find the magnitude of vector u, for instance, and then you find the magnitude of 3u, it is going to be 3 times larger. So there is going to be that direct correlation between them with your magnitudes, but you can always calculate both of them and compare, are they in fact 3 times larger or not. Okay. And that was basically the overview then of those first 2 lessons. So if you weren't there that Monday, or if you've forgotten everything about the introduction of vectors, there you have it.